Electrical drawings and diagrams are essential tools for understanding and working with electrical systems. They provide a visual representation of the circuits, components, and connections within a system. Mastering the ability to interpret these drawings is crucial for electricians, engineers, and anyone involved in electrical work. There are several types of electrical drawings, each serving a specific purpose. Firstly, we will discuss single-line diagrams. These diagrams use single lines to represent entire power systems, simplifying the representation of complex circuits. They typically show the main components, such as transformers, generators, switchgear, and major loads, along with their ratings and interconnections. Single-line diagrams are useful for understanding the overall system configuration and power flow. Secondly, we will discuss schematic diagrams. These diagrams show the electrical connections and functions of a specific circuit using standardized symbols for each component. They illustrate how different components are interconnected and how the circuit operates. Schematic diagrams are essential for troubleshooting, designing, and understanding the detailed operation of electrical circuits. Thirdly, we will discuss wiring diagrams. These diagrams depict the physical arrangement of wires and components within an electrical system or piece of equipment. They show the exact wiring connections between different parts, including wire colors, terminal locations, and cable routing. Wiring diagrams are critical for installing, maintaining, and repairing electrical equipment. Now let's discuss components and symbols. Electrical drawings use standardized symbols to represent different components. These symbols are defined by organizations like the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. Understanding these symbols is essential for interpreting electrical drawings correctly. Some common symbols include resistors, represented by a zigzag line or a rectangle, capacitors, represented by two parallel lines, inductors, represented by a coil or a series of loops, switches, represented by a line connecting to another line with a brake and a lever, transformers, represented by two coils separated by parallel lines, motors, represented by a circle with an M inside, generators, represented by a circle with a G inside, and grounding points, represented by a series of horizontal lines decreasing in length. Furthermore, let's discuss the conventions and notations. Electrical drawings adhere to specific conventions and notations to ensure clarity and consistency. These conventions include line types, such as solid lines for conductors and dashed lines for control wires, wire numbering and color coding, which help identify individual wires and their functions, component identification, which uses alphanumeric designations to label components, voltage and current ratings, which indicate the operating parameters of components and circuits, and notes and legends, which provide additional information and explanations about the drawing. Wire numbering and color coding is especially important. Wires are typically identified by numbers or letters to indicate their function and destination. Color coding is used to further distinguish wires and simplify troubleshooting. Common color codes include black for ungrounded conductors, red for ungrounded conductors in a multi-wire circuit, blue for ungrounded conductors in a three-phase system, white or gray for grounded conductors, and green or bare for grounding conductors. Let's talk about reading and interpreting electrical drawings. Reading electrical drawings requires a systematic approach. Firstly, start by identifying the type of drawing, whether it's a single-line diagram, a schematic diagram, or a wiring diagram. Secondly, locate the title block, which contains essential information such as the project name, drawing number, revision date, and scale. Thirdly, familiarize yourself with the symbols and notations used in the drawing. Refer to the legend or symbol list if needed. Fourthly, trace the circuits and connections to understand the flow of electricity and the function of each component. Fifthly, pay attention to the wire numbers, color codes, and component identifications to ensure accuracy. Lastly, use a multimeter or other testing equipment to verify the connections and voltages if necessary. Troubleshooting electrical circuits using drawings involves a logical and methodical approach. Firstly, start by reviewing the electrical drawings to understand the circuit's design and operation. Secondly, identify the symptoms of the problem and narrow down the possible causes. Thirdly, use a multimeter or other testing equipment to check voltages, currents, and resistances at different points in the circuit. Fourthly, compare the measured values with the values indicated in the drawings to identify discrepancies. Fifthly, isolate the faulty component or wiring and replace it with a new one. Lastly, test the circuit to ensure that the problem has been resolved. The importance of safety cannot be overstated. When working with electrical systems, safety should always be the top priority. Firstly, always disconnect the power before working on any electrical equipment. Secondly, use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, follow the National Electrical Code, or NEC, and other applicable safety standards. Fourthly, never work on live circuits unless absolutely necessary and only if you are qualified to do so. Fifthly, double-check your work to ensure that all connections are correct and secure. Let's talk more about the National Electrical Code, or NEC. The National Electrical Code, or NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It provides detailed requirements for various aspects of electrical installations, including wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the National Electrical Code, or NEC, is essential for ensuring the safety of people and property. Some key aspects of the National Electrical Code, or NEC, include conductor sizing, which specifies the minimum size of conductors based on their capacity and the load they will carry. Overcurrent protection, which requires the use of circuit breakers or fuses to protect conductors and equipment from overloads and short circuits. Grounding, which ensures that electrical systems are properly grounded to prevent electric shock hazards. And wiring methods, which specifies the types of wiring allowed in different locations and applications. Let's delve deeper into conductor sizing. Conductor sizing is determined by the ampacity of the conductor, which is the maximum current it can carry safely without overheating. The National Electrical Code, or NEC, provides tables that list the ampacity of different types of conductors based on their size, insulation type, and ambient temperature. To determine the appropriate conductor size, you need to calculate the load current and apply any necessary correction or adjustment factors for ambient temperature, conduit fill, or other conditions. For example, National Electrical Code, or NEC, Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 600 volts, not more than 3 current-carrying conductors in a raceway or cable or earth, based on ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit. If the ambient temperature is higher than 30 degrees Celsius, a correction factor must be applied to reduce the allowable ampacity. Similarly, if there are more than 3 current-carrying conductors in a raceway or cable, an adjustment factor must be applied. Let's delve deeper into overcurrent protection. Overcurrent protection is provided by circuit breakers or fuses, which are designed to interrupt the flow of current when it exceeds a predetermined value. Circuit breakers are reusable devices that trip open when an overcurrent occurs, while fuses are one-time devices that melt and break the circuit. The National Electrical Code, or NEC, requires that overcurrent protection devices be sized to protect the conductors and equipment they serve. The size of the overcurrent protection device should not exceed the ampacity of the conductor it protects. For example, a 14 American wire gauge or AUG copper conductor with a typical insulation has an ampacity of 15 amps, so it should be protected by a 15 amp circuit breaker or fuse. A 12 American wire gauge or AUG copper conductor with a typical insulation has an ampacity of 20 amps, so it should be protected by a 20 amp circuit breaker or fuse. A 10 American wire gauge or AUG copper conductor with a typical insulation has an ampacity of 30 amps, so it should be protected by a 30 amp circuit breaker or fuse. Let's delve deeper into grounding. Grounding is a critical safety measure that ensures that electrical systems are properly connected to earth, providing a low impedance path for fault currents to flow back to the source. This helps to prevent electric shock hazards and minimize the risk of fire. The National Electrical Code, or NEC, requires that all electrical systems be grounded, and it specifies the methods and requirements for grounding different types of systems and equipment. Grounding systems typically consist of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding conductor that connects the equipment to the grounding electrode. The grounding conductor must be sized according to the National Electrical Code, or NEC, tables based on the size of the ungrounded conductors. Let's delve deeper into wiring methods. The National Electrical Code, or NEC, specifies the types of wiring methods allowed in different locations and applications. Common wiring methods include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMT flexible metal conduit, or FMC, non-metallic conduit, or PVC, and cable assemblies such as non-metallic sheet cable, or NM cable, and armored cable, or AC cable. Choice of wiring method depends on factors such as the environment, the type of building construction, and the voltage and current levels. For example, rigid metal conduit, or RMC, is typically used in hazardous locations or where mechanical protection is required, while non-metallic sheet cable, or NM cable, is commonly used in residential wiring. Understanding voltage drop is also critical. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code, or NEC, recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, the load current, and the conductor resistance. The formula for voltage drop is voltage drop equals current times resistance. To minimize voltage drop, you can increase the conductor size, reduce the conductor length, or use conductors with low resistance. Furthermore, understanding short-circuit current calculations is crucial. Short-circuit current is the excessive current that flows in the circuit during a short-circuit condition. Short-circuit currents can be very high and can cause damage to equipment and conductors. It is essential to calculate the available short-circuit current at different points in an electrical system to ensure that the overcurrent protection devices are properly sized and can safely interrupt the fault current. Short-circuit current calculations involve complex formulas and require detailed information about the electrical system, including the transformer impedance, conductor impedances, and motor contributions. Software tools are often used to perform short-circuit current calculations. Let's talk about arc flash hazards. Arc flash is a dangerous electrical phenomenon that occurs when a short circuit creates an arc of electricity in the air. Arc flashes can generate extremely high temperatures and pressures, causing severe burns, injuries, and even death. It is essential to understand arc flash hazards and take appropriate precautions to prevent them. Arc flash hazard assessments involve calculating the incident energy and the arc flash boundary at different points in the electrical system. The incident energy is the amount of heat energy that a worker would be exposed to during an arc flash event. The arc flash boundary is the distance from the arc flash source at which the incident energy is equal to 1.2 calories per square centimeter, which is the threshold for second-degree burn. Personal protective equipment, or PPE, is required when working within the arc flash boundary, based on the calculated incident energy level. Lastly, always remember continuous learning. The field of electrical technology is constantly evolving, with new technologies, standards, and regulations being introduced regularly. It is essential to stay up to date with the latest developments by attending training courses, reading industry publications, and participating in professional organizations. Continuous learning will help you improve your skills, knowledge, and competence, and it will ensure that you are able to safely and effectively work with electrical systems.